The moon is actually twice as radioactive as the surface of Mars, and this single measurement changes everything we thought we knew about surviving in space. How can a world that is only 3 days away from Earth be more dangerous for a human being than a planet that takes 9 months to reach? This is the title question we are answering today, and by the end of this video, you will understand why the proximity of the moon is a dangerous illusion that hides the most lethal environment in our solar system. We usually think of the moon as our backyard, but the data proves it is a radiation trap that delivers a dose of 1.3 millisieverts every single day, which is nearly double the radiation level measured on the surface of Mars. This is the core spark that forces us to reevaluate our future in space, because it means the moon lacks the one invisible shield that Mars actually possesses. While the moon is closer for a rescue mission, it is far more likely to kill an astronaut before that rescue can even leave the launch pad. We have long believed the moon was the safer stepping stone because it is close enough for a quick trip home. But the physical reality of the lunar surface is a relentless assault of heavy ions and microscopic bullets that Mars partially filters out. We are going to look at the hard measurements from the Chang E4 lander and the Curiosity rover to show why the moon is not a training ground, but a survival extreme that defies our expectations. This shift in understanding starts with the simple fact that the moon is a naked rock sitting in the middle of a cosmic shooting gallery, with absolutely no protection from the stars above. The default story we have been told for decades is that the moon is the logical first step for humanity because it is close and familiar. We assume that because we can see the moon with our naked eyes and reach it in 72 hours, it must be more forgiving than the red deserts of Mars, which are millions of miles away. This old model focuses entirely on the logistics of distance and the comfort of being near Earth, while ignoring the actual physics of the environment. We dismiss the contradictions in this model because we want to believe that the easiest destination is also the safest one, and we often treat the vacuum of space as a uniform danger that is the same everywhere. However, when we look at the actual data collected by instruments on the lunar and Martian surfaces, we find a massive gap between our assumptions and the measurable truth. The moon is not just a closer version of Mars. It is an entirely different class of lethal environment because it lacks even the most basic physical barriers to space radiation and debris. This means that an astronaut on the moon is exposed to the full, raw power of the sun and the galaxy in a way that an astronaut on Mars is not. This is not a theory, but a conclusion forced by the measurement of the particles hitting the ground on both worlds. To understand why the moon is so much more dangerous, we have to look at the measurement of radiation that occurs when there is no atmosphere. On the surface of Mars, there is a very thin layer of carbon dioxide that most people dismiss as being too thin to matter, but the Curiosity rover proved this is wrong. That thin Martian air acts like a shield, equivalent to several meters of rock or a thin sheet of aluminum, slowing down incoming particles and blocking the most frequent solar events. The moon has zero atmosphere, which means every single solar flare and cosmic ray hits the surface with its full original energy. When the Chinese Chang E4 lander measured the radiation on the far side of the moon, it found a rate of 1.3 millisieverts per day. For comparison, the Curiosity rover on Mars measured only 0.7 millisieverts per day. This means that a human standing on the moon is absorbing nearly twice the biological damage every hour compared to a human on Mars. The presence of that tiny bit of air on Mars creates a massive difference in long-term survival, making the moon a far more hostile place for human DNA. This measurement is the first major clue that our proximity to the moon does not equal safety. The danger on the moon is not just coming from the sky above, but also from the ground beneath an astronaut's feet. When high-energy cosmic rays hit the lunar soil, they do not just stop. They shatter the atoms in the ground and create a secondary shower of particles called neutrons. This process is like a cosmic splatter that bounces back up from the surface, effectively microwaving anyone standing on the moon from below. Because the moon has no atmosphere to absorb these secondary neutrons, the ground itself becomes a source of radiation that adds to the dose coming from the sun. On Mars, the atmosphere helps to dampen this effect, and the soil composition is different enough to reduce this backscatter. On the moon, there is no escape because the radiation is hitting you from every single direction at once. This secondary neutron splatter is a hidden mechanism that makes the lunar surface a 360-degree radiation oven. This means that even if you build a thick roof over your head, you are still being bombarded by the very ground you are walking on, a problem that is significantly reduced on the Martian surface. Another invisible threat that the moon fails to stop is the constant rain of micrometeorites that travel at speeds of over 100,000 miles per hour. On Earth, and even on Mars, the atmosphere acts as a protective shield that burns up these tiny space rocks long before they can hit the ground. When a tiny grain of sand hits the Martian atmosphere, the friction turns it into a harmless streak of light. On the moon, there is no friction and no shield, so these microscopic bullets hit the surface with the full force of their kinetic energy. They are moving so fast that they can punch through fabric, glass, and metal with ease. This means that every piece of equipment on the moon, from a spacesuit to a habitat wall, is being slowly sandblasted by high-speed impacts. Over time, these impacts turn camera lenses and helmet visors opaque and can cause sudden catastrophic structural failure in pressure seals. Mars has enough air to vaporize, or at least slow down, these projectiles. But on the moon, you are standing in a permanent shooting gallery where the bullets are too small to see and moving too fast to avoid. The thermal environment of the moon is another area where it proves to be far more lethal than Mars. Because the moon has no air to move heat around through convection, temperatures are determined entirely by direct sunlight. When the sun is overhead, the lunar surface can reach 250 degrees Fahrenheit, which is hot enough to boil water instantly. As soon as you step into a shadow, the temperature drops to minus 200 degrees Fahrenheit in a matter of seconds. This 500-degree temperature swing happens instantly and repeatedly, creating massive thermal stress on every material we send there. Metals and plastics that are flexible in normal temperatures can become as brittle as glass in the lunar shadow, leading to cracks and leaks that are impossible to repair. Mars has a much narrower and more manageable temperature range because its atmosphere helps to distribute heat and provide a small buffer. The moon offers no such mercy, forcing engineers to design systems that can survive a constant cycle of boiling and freezing that would destroy most terrestrial machinery in a single day. We also have to consider the length of the lunar day and night cycle, which is a significant survival hurdle that Mars does not share. A single day on the moon lasts about 14 Earth days, followed by 14 days of total darkness. This means that any lunar base must rely on massive battery arrays to survive 2 weeks of lethal cold and darkness without any solar power. During these long nights, the temperature stays at a bone-chilling minus 250 degrees Fahrenheit for hundreds of hours. On Mars, the day and night cycle is almost exactly the same as Earth, lasting 24 hours and 39 minutes. This Earth-like cycle allows for much smaller batteries and more consistent power generation from solar panels. The lunar night is not just a period of darkness. It is a 2-week survival test that requires an incredible amount of energy just to keep the lights on and the heaters running. This long duration of extreme cold makes the moon a much harder place to maintain a human presence compared to the relatively normal cycles of the Martian surface. One of the most surprising reasons the moon is more dangerous is its distance from the sun compared to Mars. Mars is roughly 50 million miles further away from the sun than the moon is, which significantly reduces the intensity of solar radiation. The intensity of light and particles follows what scientists call the inverse square law, meaning that as you get further away, the energy drops off quickly. Because Mars is further out, it receives about 40% less solar flux than the moon. This means that when the sun has a major eruption, called a solar particle event, the moon gets hit much harder and much faster. A solar flare can reach the moon in a matter of minutes, leaving astronauts with almost no time to reach a protected shelter. On Mars, the increased distance provides a longer warning time and a naturally lower dose of radiation. The moon is effectively standing right in the line of fire, while Mars has the benefit of distance and a thin atmospheric shield to mitigate the sun's most violent outbursts. The physical nature of the dust on the moon is another factor that makes it a more lethal environment than the Martian desert. On Mars, there is wind and the movement of water in the ancient past, which has tumbled and eroded the dust particles until they are relatively smooth and rounded. On the moon, there has never been any wind or liquid water to erode the soil. This means that lunar dust, or regolith, consists of jagged, glassy shards that are as sharp as tiny razor blades. This dust is so abrasive that it can grind through the pressure seals of an airlock in just a few dozen cycles and can shred the delicate lung tissue of an astronaut if it is inhaled. To make matters worse, the moon is constantly bombarded by ultraviolet radiation, which gives the dust a massive static charge. This causes the abrasive grit to cling to every surface, including suits, tools, and electronics. This static charge makes the dust almost impossible to brush off, meaning it inevitably finds its way into the habitat where it can cause mechanical failure and health problems. Mars dust is certainly a nuisance, but lunar dust is a mechanical and biological weapon designed by physics to destroy everything it touches. The lack of atmospheric pressure on the moon also creates a much higher risk during a suit breach compared to Mars. The moon is a hard vacuum, which means there is absolutely no air pressure at all. If an astronaut's suit is punctured on the moon, the pressure drop is instantaneous and total, leading to the rapid boiling of fluids in the body and immediate unconsciousness. Mars has a thin atmosphere that, while not breathable, still provides a small amount of pressure. This marginal pressure provides a tiny survival buffer that could give an astronaut a few extra seconds to patch a leak or reach an airlock. In the vacuum of the moon, there is no such buffer. The vacuum also means that heat can only be moved away from a spacesuit or a habitat through the slow process of radiation. On Mars, the thin air allows for some convective cooling, which makes it much easier to manage the heat generated by electronics and human bodies. The moon's vacuum is an unforgiving wall of physics that makes every mistake potentially fatal. in a way that Mars slightly mitigates. We must also look at the historical evidence of how lucky we were during the Apollo missions to understand the true danger of the moon. In August of 1972, a massive solar storm occurred between the missions of Apollo 16 and Apollo 17. This storm was so powerful that if a crew had been on the lunar surface or in their thin-walled spacecraft, they would have likely received a lethal dose of radiation or suffered from severe radiation sickness. The only reason we did not lose an entire crew to the sun during the 1970s was pure timing. The moon offers no protection from these events, and there is nowhere to hide, unless you have already built a deeply buried bunker. Because we are now planning longer stays on the moon with the Artemis program, the statistical probability of being hit by one of these events is much higher. We are no longer relying on luck, and the data shows that the moon is a high-stakes environment where the sun can become a killer in a matter of minutes. This history reminds us that our past success on the moon was a result of short visits and fortunate timing, not because the environment was safe. The lack of an atmosphere on the moon also creates a problem with how humans perceive their surroundings, which can lead to fatal navigation errors. On Earth and Mars, the atmosphere scatters light and creates a sense of depth and distance through haze and color shifts. On the moon, there is no air to scatter light, which means shadows are pitch black and perfectly sharp. Without atmospheric perspective, it is impossible for the human eye to accurately judge how far away a crater or a mountain really is. A rock that looks like it is a few feet away might actually be the size of a house and miles in the distance. This lack of visual cues makes driving a lunar rover, or even walking across the surface, incredibly dangerous, as astronauts can easily misjudge terrain and fall into craters or lose their way. The harsh, high-contrast environment of the moon is an optical trap that can lead to exhaustion or accidents. Mars, with its dusty orange skies and atmospheric depth, provides a much more familiar and navigable environment for the human brain, reducing the risk of getting lost or injured during surface operations. NASA and other space agencies are fully aware of these dangers, which is why they use the moon as a technology testing ground under the Artemis program. The moon is not chosen because it is easy. It is chosen because it is the most difficult environment we can reach quickly. If a piece of hardware can survive the radiation, the razor-sharp dust, and the extreme thermal swings of the moon, it will likely survive anything Mars can throw at it. The proximity of the moon allows NASA to test these systems with the ability to abort and bring the crew home in a few days if something goes wrong. This does not mean the moon is safer. It means the failures are more recoverable. The mission risk assessments clearly show that the cumulative biological damage of spending 1 month on the moon can exceed the damage of spending an entire year on Mars. We are using the moon to harden our technology against the most lethal conditions in the inner solar system, using its proximity as a safety net for an environment that is otherwise much more hostile than our ultimate destination. To answer the title question directly, the moon would kill you faster than Mars because it lacks the 3 critical layers of protection that Mars provides. The evidence from the Chang E4 and Curiosity missions eliminates the old idea that the moon is a safer environment simply because it is closer. The result shows that the moon has no atmosphere to block radiation, no air to burn up micrometeorites, and no thermal buffer to regulate temperature. While the mechanism of why the moon is so dangerous is now well understood through direct measurement, we still have no easy way to protect astronauts from the secondary neutron splatter coming from the ground. The interpretation that remains open is how we will build long-term habitats that can withstand the abrasive lunar dust and the extreme 14-day nights. The verdict is clear. The Moon is a more radioactive and physically destructive world than Mars, and its proximity to Earth is a logistical advantage that masks a much deeper environmental danger. This is not just a theory. It is the reality forced upon us by the hard data collected from the surfaces of both worlds. This realization changes how we look at our future as a spacefaring species. It means that the Moon is not just a smaller version of Mars, but a unique challenge that requires more advanced shielding and more robust engineering. When you look up at the Moon now, you should see it not as a peaceful neighbor, but as a raw and violent frontier that tests the very limits of human biology and technology. We are going back to the Moon, not because it is the path of least resistance, but because it is the ultimate stress test. If we can conquer the Moon, we will have proven that we can survive the worst that the solar system has to offer. The data from NASA and other global space agencies has pulled back the curtain on the lunar illusion, showing us that the most dangerous place in the void might be the one that is closest to home. This forensic look at the lunar environment reminds us that in space, distance is not the only measure of danger, and the most familiar sights can hide the most lethal secrets. As we move forward with the Artemis missions, we do so with the knowledge that the Moon is a fierce teacher, and the lessons we learn there will be paid for in the hard currency of survival against the most hostile conditions we have ever encountered. If you found this deep dive into the hidden dangers of the Moon and Mars valuable, consider following for more analysis of the data that defines our future in the stars.